Here. All right, guys, so I turn the conversation to you. As we gather back together after the weekend, we are looking first, again, at this 30,000-foot view of acid-base chemistry. We'll address questions here. Then, guys, today, very short. We are going to look at redox chemistry, and then there are some other things we are going to get done today just because we're going to have time. And then, remember, Thursday will be the last of the new material, and then the next day that I see you after the long Labor Day weekend, we'll be taking our test. So, guys, with that said, what do you need to talk about? Acids and bases. Yeah? Sure. Hold on, let me interrupt. Are you leading us to a particular question or just a general idea? That's okay. Yeah, then let's go general first.
Okay, so like with the hydrogen for ionized hydrogen, it's like an H+.
Yes.
Like you said, it's just a proton, right?
Yes.
I'm so confused on that. Like, what even acids and bases? I didn't know what it was to do with like an H+.
Okay, so I'm not exactly sure where you're headed with that. I know. So what if we draw a picture? All right. So somewhere in amongst your ramblings, the question was protons and doesn't it change stuff, right? Okay, so let's do this. Let's actually make this a little more complicated. So we have HNO3, nitric acid, right? And then we have NH3, which you should remember is a base. So, guys, what happens when one acts as the acid and the other the base? And the answer is the acid gives away a proton, gives away a hydrogen ion. Where does it go? It goes to the base. And when that happens, this proton goes over here, and when it does, one of the products, and you may remember the term for this is what is called our conjugate base. It's the thing that the acid turns into. Our conjugate base is nitrate, and then our conjugate acid is ammonium. But now let's dig into this a little deeper. So what does this look like? And so it looks like this. So that is literally what a nitric acid molecule looks like. It's not ionically bonded. It's all covalently bonded. We've got that NO3 ion, and then bonded to that is a hydrogen atom, and that would be nitric acid. Then our other reactant, is the ammonium ion, or the ammonium molecule, which looks like this. Is that okay? Okay, so guys, what does this chemistry look like? And the answer is this. This bond right here breaks, and that hydrogen nuclei, that proton leaves. So when that happens, what happens is this guy, that hydrogen, leaves, but it leaves its electrons behind. That is why nitrate takes on a -1 charge. The hydrogen atom leaves its electron behind, the electron that formed the covalent bond to nitrate, and this dude leaves, that electron stays behind, and that then gives us the nitrate ion. But where does the proton go? And this is where this gets kind of weird, because guys, this is just a proton. It's a hydrogen nuclei. It is a little bundle of positive charge. It's a proton. So that proton is looking for something to be attracted to. Well, guess what it's attracted to? Those two unbonded electrons on the nitrogen. So when this bonds, what happens is this proton, which is positive, is then attracted to these two unbonded electrons on nitrogen, which are negative, they're electrons. And when they get together, these guys bond together. I'll represent it again as a hydrogen atom, a proton, and then this bond forms, and that's where ammonium comes from. So yeah, it absolutely changes things. When the proton leaves, it leaves electrons causing a charge, and then that proton is then attracted to something negative, like the electrons on the nitrogen, and then that forms a positive ion, which we call ammonium. Was that anything like what you wanted to talk about?
That's how anything like I said, I probably should know this, but like, in knowing that, like,
Yeah.
how would you just look at a compound and know it as a base? Like, you don't use the hydrogen.
Yeah, that's a really good question. So again, it's these questions about how are we supposed to know that, right? So these are the things. So guys, the question on the table now is, how can you just look at something and know that it's a base? So guys, let's review really quickly. There are only right now, there are only two kinds of bases you need to keep track of. One of them are the group 1 and heavy group 2 hydroxide salts. So those are called the strong bases. And those would be group 1 and the heavy group 2 hydroxides, right? Those are ionically bonded: lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium hydroxide. Then the other ones that you need to know are the weak bases. But right now, the only weak base that you need to be aware of is NH3. With that said, a larger principle is nitrogen. If you look at where nitrogen is on the periodic, that was a mess, hold on a second. Where you look at where nitrogen is on the periodic table, it's got 5 valence electrons, right? So what nitrogen does is it has a pair of electrons, and then it's got 3 spaces that are available for bonding. So when nitrogen forms molecules, it'll form 3 bonds, and then it'll have this unbonded pair of electrons, which you just saw makes it attractive to protons. So when you see nitrogen, there should be something in your brain that's going, that's got to be a weak base. Because nitrogen in acidic context will typically be a weak base. So that's all you need to know right now. Nitrogen forms a weak base, and then the strong bases are the hydroxide salts that dissolve in water. Is that okay?
That's kind of on the whole, like CH3CN.
And that's it. It's the N. It's the N that tells you that it's a base. And now you know why. It's that unbonded pair of electrons. Christian, go ahead. Yeah. So, are we good? Oh. Yeah, I think it's this one right here. That nitrogen makes that molecule basic. Weakly basic, but basic. Correct. Right. Yeah, and then you got to be careful because this is a weak acid because it's not one of the 7. Yep, exactly. And then this doesn't contain hydrogen at all, or nitrogen. That's a salt. And then here's classic strong, yeah. You could definitely have approached it that way, but now maybe because of the conversation we just had, when you see nitrogen, you should be thinking weak base. Okay. Obviously not, though, in a case like this, right? Like if you've got HNO3, that's different, but yeah, okay. Exactly, yeah, yep. Go ahead, Ben. Oh, you're stretching. So, guys, what else would you like to talk about? Yeah, please. Appreciate it. 41 Bravo. Oh, shoot. I'm drawing dots. 41B? What about it? Okay. So, guys, allow me to talk about A as well, so long as we're here. Guys, there are some things in this class that you just have to memorize. You're becoming comfortable with that. And guys, one of the things that they just expect you to know are what are called the gas-forming acid reactions. And that is represented in 41A and 41B. So, guys, what you need to do is you need to tune your spidey senses so that when you see these two particular situations, your spidey senses go, oh my gosh, this is something I'm supposed to know. So, guys, what are those things? Well, first of all, you got to have acids. And they make it easy for you. They make it one of the 7 strong acids because those are things that definitively you should know are acids. But then this is the spidey sense part. You see sulfur, your brain should just start to fire. And guys, if you see carbonate or bicarbonate, your brain should also start to fire because these are the gas-forming reactions. So, Brescia, it was you that asked about this, right? Okay, so let's do B first, but I'd still like to come back to A. So, when we look at letter B, we've got an acid and we've got a carbonate. Guys, at this point, we should be going, wait a minute, this is gas forming. So, how do you deal with this? And this is the answer. First thing you've got to do is you've got to form a salt. Here, let me step back even more. This is a double displacement reaction. The magnesium hooks up with the ClO4, and then the hydrogen hooks up with the carbonate. When that happens, your products are magnesium chlorate and then the carbonic acid molecule. We're not even going to balance the equation right now, but these are our products. But then here's the trick. This doesn't stick around. This immediately breaks down, and we represent it as its products, which are carbon dioxide and water. And this is where our gas comes from. So now we've got our salt, our gas, and our water, and that's these. The only difference is that the ClO4 is actually a spectator, so it goes away. But when you see carbonate, you're always thinking there's got to be carbon dioxide and water because the acid and the negative ion from the carbonate hook up and they make H2CO3, which then breaks apart. Is that okay? Yeah, good. Again, we're careful with always and never, right? But yes, yeah, especially in these instances because the carbon dioxide can bubble away so it never reaches equilibrium. Absolutely. Christian, go ahead. Carbonic acid. The H2CO3 is called carbonic acid, and that's what's breaking apart. So guys, let's then go to letter A. So this is where we've also got in a situation where we have an acid and now we have sulfur. When we see that, we need to immediately realize that we're forming H2S gas. So again, double displacement reaction. The CD, the cadmium, hooks up with the sulfate, and the hydrogen hooks up with the sulfide. And so here we get our H2S gas. The sulfate is actually a spectator, and then we end up with cadmium ion also in solution because the cadmium starts as a solid and then it becomes an ion in solution. But again, we're looking for that gas, which is H2S. What else, y'all? Yeah? Yeah. That's a great question, and actually the answer is this. Again, you know I love to draw pictures, and nothing makes me happier than a good beaker, right? So it actually looks like this. So magnesium carbonate doesn't dissolve in water. It's a solid. So what we actually have going on here is we've got a pile of magnesium carbonate that doesn't dissolve. It's a solid. And then to this we add HCl-ClO4 acid. And as we add the acid, we understand that acids are dissolved in water. So what's going on is magnesium is not a spectator because it doesn't start as an ion. It actually starts trapped up in the crystal of magnesium carbonate. As the reaction goes on, the magnesium does become an ion in solution, but because it doesn't start there, it's actually doing chemistry, so it's not a spectator. Is that okay? Yeah, what you guys ask good questions. Keep going, Santiago.
Even the weak acids needs to be like dissolved in water to be an acid?
Correct. Yeah. So for us in this class, and guys, you should hear this. You understand? I think you understand this, guys. The class that we call AP Chemistry is first year college chemistry, which is inorganic chemistry. So in this class is meant to replicate a first year inorganic chemistry class. And in that setting, all of our acid-base chemistry is in water. Weak or strong doesn't matter. Understand that your sophomore year, you will then take organic chemistry, and then that rule about acids and bases having to be present in water completely changes. But in this class, in inorganic chemistry, it's always in water. Okay. All right. Guys, what else? Yeah. 2. Question which? Yeah.
I understood it. I was like, I went to the chapter of zoning, I guess. It's not all the kids who call the acids or the bases that it's basic or
Sorry, I'm scrambling to catch up with your thoughts. So let's just talk about the terms. So when we...
just like, is there always greater concentration of hydroxide in dibasic versus monobasic, and always greater concentration of
Yeah, so the answer is probably going to be more complicated than maybe where you're going with this. But let me give you the real answer, and then we'll talk about it the way I think you're thinking about it, okay? So, for example, if we look at the salt magnesium hydroxide, that is what we call a dibasic salt. It's got 2 hydroxides, right? But that in water creates no concentration of hydroxide because it doesn't dissolve. Okay, so when we say, because you were using the word concentration, and when you say concentration, that begs the idea that it dissolves, and this doesn't. With that said, this is a phenomenal base because it has 2 hydroxides available. So, and oh wait, where'd it go? Wait for it. Oh, there. Oh, that was carbonate. Never mind. Shoot. Wrong base. All right. So the idea is that if we have a beaker, and if in that beaker at the bottom we have magnesium hydroxide, that doesn't dissolve in water. But if we dump an acid into that, like if we were to take this and if we were to dump hydrochloric acid into that, the magnesium hydroxide would neutralize that hydrochloric acid like crazy because it's got a ton of hydroxide available. It just doesn't dissolve in water. So, coming back to your thought, maybe we need to get rid of the word concentration. So dibasic bases are better at neutralization than monobasic bases like sodium hydroxide, which is just NaOH. So is there a relationship between the amount of hydroxide and how well it functions as a base? Absolutely. But it's not a... Yeah. Yeah, and that's... Yeah. Right, and that's because it is one of the strong ones and it does dissolve in water, but it releases 2 hydroxides for every formula unit. Yeah. With fluoride? You're obviously looking at a particular question.
I knew that already, like going back to I think it was number 5,
Yeah. Okay, so when you say what's going on with fluoride, do you mean in the context of acids and bases? Yeah. Yeah. So we're going to spend an entire day on this in February, but let's talk about it right now. So here's what's going on. We've got iodine, bromine, chlorine, fluorine, right? And we understand that these halogens form strong acids. HI, HBr, HCl, all strong acids, right? But not HF. The question is why not, right? What is up with fluoride? And the answer is this. So let's take, for example, well, here, let's just do them all. So we got HI, we've got HBr, and we've got HCl drawing in the rest of the electrons. So those three molecules are all strong acids, right? So here's the question. What makes them strong? They completely break apart. So what that means is this bond and this bond and this bond breaks like crazy. And because those bonds break like crazy, that makes these things strong acids. Do you see where this is headed? If you look at hydrofluoric acid, fluorine is the most electronegative element on the periodic table. It is so stinking electron hungry that what happens is, because it's such a strong electron attractor, it creates such a strong bond with hydrogen that it doesn't break very well. So, it's too strong, forming a bond with hydrogen that is so strong that it doesn't break easily, and therefore it makes HF a weak acid. Does that make sense? The opposite. This is the one that's almost ionic. It is so polar because fluorine is so strong. This is actually the bond that is moving very close to being ionic. These are much, much more covalent, which is actually what makes them weaker. Exactly. Correct. You're exactly right. Yep. Yeah, Isaac. It is. Go ahead. Yeah, that's a really good question, and the answer is yes. Increasingly now we have it's fascinating. Maybe some of you might want to get into this. It's actually what's called computer computational chemistry. So we can actually now model molecules without ever building them in a lab. We have the ability to keep track of all of the variables and all of the constraints that cause these molecules to do what they do, but instead of building them, we can actually model them computationally on a computer, and it works. So we could model these things and easily go, this would be strong, this would be weak. The math and the modeling is difficult, but now we've got computers that can do it. So yeah, absolutely. What else, y'all? We done? Please.
Does that mean that hydrogen ionized faster?
Now be careful with fast. So fast is rate, and rate, guys, don't miss this. Fast is rate, and rate is dependent. I should be able to ask you, what is rate dependent upon? Temperature, surface area, and concentration. Remember that from last year? So be careful with rate. The speed at which these things breaks down has nothing to do with whether they're weak or strong. Speed is about temperature, surface area, and concentration. Don't confuse that with completion. So you can go to completion really slow or really fast. And they love to nail you on that on the AP test because kids get these mixed up in their brain. Speed and completion have nothing to do with each other. A reaction can reach equilibrium really fast, or a reaction can go to completion really slow. They're completely unrelated. So, what else, you guys? Are we done? Okay, so let's get this recorded. Pause it. Oh, you guys are so helpful. Shoot. There we go. So, yeah, August 31st, right? Which means that we are going to get in 3 weeks of school before Labor Day. If ever there has been a need for a constitutional amendment, I believe this could be it. There have been some significant challenges that have faced our country. Prohibition, women, what? I would suggest that this should make the cut. Guys, you can't do 3 weeks of school before Labor Day. It's immoral. I know. Believe me, I know. We need to do something about this. No, don't try to cast a positive light on this.
We'll still be here.
Don't do it. You can justify away anything, or you can get mad. All right, so guys, we talked last time about this idea of a 30,000 foot view. That's what we're doing here. Allow me, if you will, to paint a picture. It's mid-March, third week of March. The flowers are starting to bloom. The weather is getting warm. Spring sports are starting into their seasons. We're looking forward expectantly to spring break. And guys, this magic thing is going to happen. And you will get up and you will turn into the basket your very last chapter summary of the year. It will be chapter 20. And it will be all about electrochemistry. And then, guys, we will start a very brief 3-day unit on electrochemistry. And the very first thing that we are going to talk about is oxidation reduction. And guys, when that happens in March, I'd like you to think back to today because it's going to go fast. But guys, what I'm telling you is the next time we talk about this, we're going to be 3 days away from the end of the year in this class. And it goes fast. So guys, understand again today what we're going to do is a 30,000 foot view, right? It's very introductory, it's very superficial, and then we will do a deeper dive on this when we get together in March. So guys, with that said, what do you need to know about oxidation reduction reactions in order to be at least conversant enough in this that we can talk about this until we get to March and really get into it? And guys, the first thing we need are some definitions. These are the basics. That would have been funnier had I said that in the previous topic because guys, I know. So guys, oxidation. Very well, when we get into this again in March, you will find that this becomes a term you don't even have to think about. You can simply look at processes and go, that's being oxidized. But for now, guys, it's kind of like especially if you've had siblings that have learned like languages on their missions. You know that you have really come to appreciate and understand the language when you're no longer thinking it in English and then translating it, but you're actually thinking it initially in the other language. So guys, for now, when you think about oxidation, your brain may have to go through the process of thinking oxidation is the loss of electrons. Consequently, this is being oxidized. But guys, very quickly, this term at the end of the year will become a part of your vocabulary, and you'll just be able to look at something and go, that's been oxidized. But guys, the question then becomes, what does it mean to be oxidized, and how do we know that something's been oxidized when we can't actually see electrons? And guys, the answer is we look for evidence. And the evidence that we look for is a change in charge, specifically a charge becoming positive. So guys, oxidation means the loss of electrons. And when something loses electrons, its charge, not surprisingly, becomes positive. And so that's what we look for when we think about oxidation. Now, so guys, just so you're clear on this, we can talk about it briefly. Guys, why do we call oxidation, let me say that backwards. Why do we call the loss of electrons oxidation? What word is sort of at the root of oxidation? Oxygen. Keep going, because actually those were, so guys, the first oxidation reactions that we studied were rusting. But go full circle with that. Guys, why would the loss of electrons be tied to a process that is named after the element oxygen? Think about what you know about oxygen. Good. Guys, oxygen is a really good electron taker. So let's talk about why. Notice where oxygen is on the periodic table. How many valence electrons does it have? How many does it want? 2. So it's good at taking in electrons one by number. It's got space for 2, so it's not just doing onesies like the halogens. It can take them in 2 at a time. But guys, what else is it about oxygen that makes it a good electron taker? It's very electronegative. Guys, it's very high on the periodic table. It's small, it's compact, and it's a really good electron stealer. But guys, there are other elements on the periodic table that are similarly small and have room for electrons. So why, when they originally were studying this removing of electrons, did they settle on oxygen? And guys, the answer is because it's also plentiful. And that's where we get to rust. So guys, all rusting processes, and we'll look at this in a minute, all rusting processes are actually oxidation processes. Oxygen is stealing electrons from metals and forming the metal oxides of these metals, and that's what we call rust, but it's an example of oxidation. So, with that said, where do the electrons go? So, if something losing electrons is oxidation, how do we describe the thing that's gaining the electrons? And the answer is reduction. Guys, reduction is the gaining of electrons by a substance. But guys, why would we call that reduction? What happens to the charge of the thing that's gaining electrons? It goes down. It's reduced. So the charge of the thing that's being reduced goes down. So how then are you going to remember that oxidation is the losing of electrons and reduction is the gaining of electrons? Well, guys, there's a couple ways that you can do this. I actually fall back on this if I get confused. The charge of the particle that's being reduced is reduced. So the charge of the thing that's being reduced is going down. At the University of Utah, they actually teach this. They use the oil rig acronym. So guys, oil rig stands for oxidation is loss, reduction is gain. But however you choose to remember this, guys, for now, if you can fall back on one of these and if you can go, okay, whoever lost electrons is oxidized. But again, when we get back to this in March, it's going to be much more about, you're just going to use these words conversantly. Okay, so guys, with that as a foundation then, we need to bring the pieces together. Because the bottom line is this. You can't lose electrons without them having somewhere to go. And you can't gain electrons without somebody losing electrons. So guys, you will never have oxidation without reduction or vice versa. So when we pull these together, we call this process redox. Redox is the accepted contraction for what we call oxidation-reduction reactions. So guys, oxidation-reduction reactions then are processes in which electrons are exchanged between substances. Now again, when this happens, we are looking for charge changes. And this is the first thing that we've got to dig into a little more deeply. So guys, this you may find initially challenging, but you'll get better at it as we go. In order to figure out what is being oxidized and what is being reduced, you need to know the charges, which we call oxidation numbers, of every single atom in a compound. In order to do that, you need some rules. So guys, I would encourage you to write these rules down. These are the rules for signing oxidation numbers. There are 6 of them. Rule number 1 is this. All atoms in their elemental form have an oxidation number of 0. So guys, if you have an element, that element has an oxidation number of 0. So guys, just a second. So for example, this is a vial of graphite, which is pure carbon. So guys, what is the charge of each one of these carbon atoms? And the answer is 0. Because they're in their elemental form, they have the same number of protons as they do electrons, and their oxidation number is 0. Now guys, what about this? You all should know that oxygen is diatomic. That is oxygen in its elemental form. You never find oxygen by itself. So when oxygen is hanging out with other oxygen atoms, they bond together in packages of 2. Because that's true, that is the elemental form of oxygen, and the oxidation number for that is also 0. So whether it's diatomic or not, in its elemental form, their oxidation numbers are 0. Yeah? No, but it's actually not something you write out frequently. You'll be okay. All right, so guys, rule number 2 is this. Whoa. Rule number 2 is this. For any monatomic ion, the oxidation number is equal to the charge of the ion. And you read that and you go, what the crap does that mean? I'll show you. I'll show you. So guys, for any monatomic ion, the oxidation number is equal to the charge of the ion. So guys, let me show you what this means. So imagine let's do this. Whoa! Look away. All right. So guys, here's an example. Take, for example, magnesium chloride. Please, in your notes, put this in a beaker of water. What does magnesium chloride break into when it dissolves in water? So we're going to get magnesium, and we're going to get chloride, and we're going to get chloride. Right? But this is wrong. What's missing? Charges. So, guys, you may have noticed that, for example, you know magnesium is +2, right? And you may have noticed that sometimes I'll write that +2, and sometimes I'll write that 2+. So the question is, which one is it? And the answer is, we can use them interchangeably. That's what this is saying. So let me explain what this means. Guys, when we write the charge first and the number second, this is an oxidation number. So Maddie, there you go. We're going to abbreviate it like that. This is an oxidation number. This tells you the number of electrons that an atom shared. This is an ionic charge. This tells you the number of electrons that an atom lost or gained. And guys, when you get to university, you are going to have professors that will not let you do this haphazardly. If you have an atom that is in a covalent bond, that is electron sharing, that's an oxidation number, and you've got to put the charge first and the number second. If you are in an ionic bonded setting, that is a number of electrons lost and gained, and then it's number first, charge second. So technically, if we add magnesium, this magnesium should be magnesium 2 plus, because magnesium chloride is ionically bonded and it is losing electrons. So that should be the number and then the charge. But guys, for most situations, these are interchangeable. And as a result, you've noticed that I do either one of these because they're typically interchangeable. The number of electrons that an atom shares is typically the same as the number of electrons. The number of electrons that an atom shares is typically the same as the number of electrons it loses or gains. So we use them interchangeably, but understand at the university level, they will many times not let you get away with that because there's other things going on. So, yeah.
So are we going to want to generally default to the Ionic Equation?
Yeah, so, yes. So, this is where I get, so, let's say, so if you want to do it right, if it's a salt, you're going to do this. If it's a molecule, you're going to do this. With that said, most of the time, especially in chapter 4, it's always going to be salts because it's aqueous solutions, right? And then it'll be the bottom one. I was about to say yes to your question when you said, should we just default to the bottom? The problem is when we get into molecular structures, we're going to start calculating what are called formal charges. And when we calculate formal charges, it's actually oxidation numbers, which are the top ones. So give yourself some freedom. You can do it either way. The AP graders won't nail you for it. But if you really want to do it right, this is for salts and that's for molecules. Is that all right? So guys, let's keep going. Next idea is number 3. Non-metals normally have negative oxidation numbers. Non-metals normally have negative oxidation numbers. Can you think about why? Where are the non-metals on the periodic table? Left or right? The right. So they're small and they're strong and they take in electrons. That makes them negative. Then guys, hydrogen can be +1 or -1. If hydrogen is bonded to a non-metal, the non-metal is stronger. It will attract the electron, making hydrogen positive. If hydrogen is bonded to a metal, then typically the hydrogen will attract the electron, and that makes it negative. Then guys, the last 2 rules. The sum of the oxidation numbers for all the atoms in a compound is 0. They're neutral, so all the oxidation numbers have got to sum to 0. But then guys, this gets a little tricky. The sum of all the oxidation numbers in a polyatomic ion adds up to the charge of the ion. And now you're going, oh boy. I'll show you an example. And then guys, we'll wrap up the day. How you doing? You guys okay? So guys, let me show you what this means. Am I okay to switch pages? Can this go away? You're still writing. Hurry! You done? How about now? How about now? You done? All right. So guys, potassium permanganate. when we get into March, you're going to find out the potassium permanganate loves to do redox chemistry. You don't need to know that now, but we do need to be able to take a substance like potassium permanganate, and we need to be able to figure out the oxidation numbers for every single element in the compound. So guys, first of all, this. Is this a salt or is this a molecule? It is a salt. It is a potassium ion ionically bonded to a permanganate ion. And guys, here's what that means. And I would encourage you to write this down big and centered. Give it a couple lines above and a couple lines below, and write it kind of freakishly big. So guys, what you've got to be able to do is you've got to be able to assign oxidation numbers to every atom in this compound. So the first thing you do is this. It is a salt. And because it's a salt, we are going to think of it, don't laugh. We are going to think of it as being two separate ions. I would encourage you to join me in underlining the ions. So now that we understand that this is two separate ions, we then need to find the charges of those ions. Is that me? No. So guys, what's the charge of potassium, element number 19? Plus 1. So we're going to go plus 1. So if potassium is plus 1, what is the charge of permanganate, KMnO4? Minus 1. I would encourage you to write it down up here. The reason is this. Guys, the entire MnO4 has a charge of minus 1. We've got to find the charges of the atoms that make it up. So now we come over here and we look at oxygen. And guys, what is the charge of oxygen? Minus 2. Now guys, check this out. Don't write anything down now, but check this out. Guys, manganese, not magnesium, manganese is right here. What's its charge? Holy smokes, right? It's got like 1,000 different charges. So what are we going to do? And the answer is this. Guys, oxygen is our fixed point. Oxygen is always minus 2 unless it's in the peroxide ion, and then it becomes minus 1, but this ain't peroxide, so never mind. Now guys, do this. There are 4 oxygens. What is the total negative charge of those 4 oxygens? Minus 8. So what does manganese have to be in order for this entire bundle to be minus 1? Plus 7. These are the oxidation numbers for these elements. Potassium is plus 1, manganese is plus 7, oxygen is minus 2. Did that make sense? Now guys, just a little foreshadowing. This is why manganese is so often involved in oxidation reduction reactions, because guys, manganese has so many different charges that it can take on that it loves to adopt different charges by gaining and losing electrons, typically losing electrons. And that's why this is such a frequent participant in oxidation reduction chemistry. But do you understand the idea of assigning charges, assigning oxidation numbers? Okay. So guys, this ends how we're going to wrap up the day. In the same way that in acid-base chemistry, you had to learn, you need to know about neutralization reactions and the gas-forming reactions. Guys, similarly here, there are a couple general oxidation reduction reactions that you need to know. So it goes like this. Generally, these reactions are single displacement reactions. And when this is the case, typically what we have is this. The metal starts in its elemental form, and you'll notice then I use the word ionized. Typically it's oxidized. but the metal begins in its elemental form, and it is either ionized, oxidized, by an acid or a salt. Oh, excuse me. So guys, we're going to look at an example of each, and then we're going to call it a day. Ready to go? So guys, the first one that we're going to do is by an acid. A metal being, ionized by an acid. So guys, can you picture it? Chemistry last year, we did the lab where we looked at reaction types. And one of the reactions that you did is you dropped a piece of zinc into hydrochloric acid, and then you captured the gas in an inverted test tube and shoved the burning popsicle stick in there and exploded, and you giggled. Remember that? I know. Yeah, right. Okay. So, guys, that reaction that was taking place in the test tube, not the exploding hydrogen gas, but the reaction that was taking place in the test tube was a single displacement oxidation reduction reaction. So, guys, let's study it. Elemental zinc was reacting with hydrochloric acid. Please write the products for this reaction and then balance it. And then please stop. And guys, I'm going to move this up a little bit. So zinc, hydrochloric acid, so guys, you should be done. The zinc hooks up with the chloride. That forms ZnCl2. Then the hydrogen is displaced, but it's diatomic. And then there's a 2. Let me center it better. Then there is a 2 here. And I believe that balances. Is that right? Okay. Now, guys, let's think about what this looks like. We had the hydrochloric acid, which is aqueous, so we actually add hydrogen ions and chloride ions, and to that we added the zinc. Zinc was a solid. Then as this reaction took place, we were creating zinc chloride. Guys, where does the zinc chloride go? Stays dissolved in the water. Where does the hydrogen go? It bubbles away. So now, guys, let's kill our spectators. Zinc started as a solid. Where does it end up? Dissolved in water. It did chemistry. Hydrogen starts dissolved in water, ended up a gas. Did it do chemistry? Yeah. What about chloride? Started dissolved in water, ended up dissolved in water. Chloride is a spectator. This then, guys, provides our net Ionic equation. Correct. Yep. Or a gas. But for sure it indicates it's not dissolved in water. Yeah, okay. So guys, let me ask you a couple questions. Let me ask you differently. What evidence do you have that this is oxidation reduction? Charge changes. Please see that. Guys, the evidence that we have of oxidation reduction are charge changes. So now there's a whole host of questions that you need to be able to answer. As I would encourage you to do this with me. Draw lines similar to these to connect your reactants and products. So guys, do this with me then. We now need to assign charges to these elements, to these species. This is +1, this is +2. What is the charge of zinc before it goes into the juice? 0. All elements in their elemental form have a charge of 0. Then guys, what about the diatomic hydrogen? What's its charge? Also 0, since this is its elemental form. Now guys, do this with me. Zinc is... Stop it! Zinc is going from 0 to +2. What causes that to happen? Is it gaining or losing electrons? Losing how many? 2. So guys, this represents the loss of 2 electrons. Now, here we have hydrogen going from +1 to 0. For a hydrogen to go from +1 to 0, how many electrons does it pick up? 1. Where did the other electron go that was lost by zinc? To another hydrogen ion. It's 2 hydrogen ions. Each of those hydrogen ions gain 1 electron, and that's where the H2 comes from. So this represents the gaining of 2 electrons in total. Does that make sense? Guys, this is what is called the law of conservation of electrons. We will talk about it more in chapter 20. But guys, understand right now, electrons in has got to equal electrons out. But the ones that I give you always will. Now guys, this. What happened? It's a weird question. The thing that happened to zinc, is that oxidation or reduction? The thing that happened to zinc, is it oxidation or reduction? Oxidation. Zinc is losing electrons. Does that make sense? Now guys, be very careful. If zinc is being oxidized, what is being reduced? I know you're scared now because I said be careful. Guys, what's being reduced? Not hydrogen. Hydrogen ion is being reduced. Guys, this is hydrogen ion, this is hydrogen gas, and they couldn't be any different. These are protons. This is a gas floating away diatomically into the air. Hydrogen ion and hydrogen are nothing like each other. So you can't confuse them. So guys, what is being reduced? And the answer is hydrogen ion. Does that make sense? You got to be careful there. So guys, this is oxidation reduction full circle. Let's try one more. By a salt. Oxidation reduction by a salt. And guys, we are going to do zinc and copper 2 sulfate. So a chunk of zinc, no, copper 2 sulfate, not 1. Zinc and copper 2 sulfate. Predict the products. What does the zinc hook up with? Sulfate. +2 -2. That's ZnSO4. And then the copper gets displaced. All by its lonesome. Now guys, we need to identify oxidation numbers. This is zinc in its elemental form, it is 0. This is copper in its elemental form, it is 0. Now guys, we've got to be careful. Don't write until we talk about this. So guys, we know here the copper is +2 And we know that sulfate is -2. But hold on. Do we need to figure out the charges of the individual atoms in the sulfate? And the answer is no. And it's a spectator. Guys, sulfate stays intact. It doesn't change. Because it doesn't change, we know that its oxidation numbers are not changing, and that also then makes it a spectator. So we don't have to muck around with sulfate because it's a spectator. But now we do need to know the charge of zinc, and zinc is +2. So now, guys, let's write the net ionic equation. Elemental zinc plus copper 2 plus ion yields zinc 2 plus ion and elemental copper. Like so. Now, guys, let's talk. In your notes, please write down, fill in the blanks. Blank is being oxidized, blank is being reduced. So guys, let's do this. Without using names, what is happening to this? Is it gaining or losing electrons? This is losing electrons. That is oxidation. So zinc is being oxidized. That means that this is being reduced. Its charge goes from 2 plus to 0. Its charge is going down. What is being reduced? Copper ion. Copper ion is being reduced. So guys, what then does this look like? In that same lab where we generated the hydrogen and giggled, we also did a portion of this lab where you took a piece of zinc and you submerged it in a couple centimeters of copper 2 sulfate solution. Well, I'll ask, do any of you remember the color of that solution? It's actually blue. You need to know that. Copper in solution is blue. Copper ion in solution is blue. And you took that piece of zinc and you dropped it into the copper 2 sulfate solution, and then you looked at it some minutes later, and the solution was less blue, and the copper looked, or the zinc looked fuzzy. If you don't remember, guys, it actually looks like this.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation reduction. When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation reduction reaction occurs. In this reaction, zinc is again oxidized.
So guys, this is actually what this looks like. The copper ion is in solution. This is our piece of zinc. These come into contact.
Now, however, copper 2 plus ion is reduced.
When they come into contact, the zinc metal loses electrons to the copper ion. The copper ion is reduced. It goes from +2 to 0. It becomes an element, and it plates onto the zinc. That was the fuzzy stuff you saw in lab. But guys, notice the zinc atoms are losing electrons. They are being oxidized. When the zinc metal is oxidized, what happens to these ions? They go into solution.
To copper metal. In the two examples we have seen, zinc is oxidized, Because
And this is a part of a bigger video.
it causes the reduction of other substances, zinc is said to be a reducing agent.
Or about
The
this.
substances that are reduced in these reactions, hydrogen ion or copper plus 2 ion, are oxidizing agents towards zinc.
And guys, we'll talk about that idea of agency in March. The thing that you need to have a handle on right now is this process of exchanging electrons as the copper ion is being reduced and the zinc ion is being oxidized. You get the idea? Okay. So guys, this then is where we are. Here's your homework. I know that you don't trust me. You think this is going to be parts A through F for each of these questions. A couple of them are. But guys, this is not a ton of homework. So here's what we're going to do. I'm going to stop recording.